Hey, welcome back to Abstract Algebra. In this video lecture, we're going to start our work in section 4.5, which is about the ring of polynomials over a field. Um, in high school algebra, you were introduced to the notion of polynomials. It's the first kind of function that you ever dealt with, and you learned how to add them, multiply them, factor them. And there in algebra and calculus, you think of polynomials as functions where the input variable is a variable, the output variable is a variable. Here we're going to be treating these things just more formally like algebraic objects. I mentioned in an online class that the kind of birthplace of group theory was about trying to study the problem of finding zeros of a polynomial. So what we're going to be doing for the remaining 8 lectures in this course is kind of trying to put that notion of zero of a polynomial in kind of a formal algebraic setting. So we're going to take it away from any kind of analytic geometry, no XY plane, no graphing functions. I want to kind of develop this all algebraically by just sort of looking at these formal expressions, these formal polynomials with coefficients in a field. So you can see the goals of this lecture here today. I want to introduce this ring of formal polynomials over a field. Here, capital F denotes a field. And so in that description of them, it may seem like I'm kind of talking about some foreign object, but I want you to just keep telling yourself these are just polynomials. You know how to add them, you know how to multiply them. I'm just kind of trying to set this up in a formal framework that we can use some of our ring theory to analyze them, okay? So I'm going to introduce that ring of polynomials. I want to carefully mean what I describe, rather what I mean by polynomials being equal. I want to give you formulas for adding and multiplying them, but again, you already know these formulas. You can add and multiply polynomials as well as I can. I also think you know what I mean by the degree of a polynomial, but I want to define it in our formal setting. And then I want to prove that the ring of polynomials is an integral domain. All right, so you remember what that means, that it's going to be a commutative ring with unity, no zero divisors. Some of these proofs about all the ring axioms and stuff, I'm certainly not going to do it. The author doesn't do it in the book. They're not difficult. They're a little bit tedious. I would kind of suggest that you pick one of them, maybe the, I don't know, associative law of addition or something like that. I'll make some remarks about them, but I'm not going to write complete and comprehensive proofs here. It would make the video 4 hours long if I did that. All right, so let's get started. You can pause this. I'm going to be talking fast. I'm trying to keep these videos so that they're not more than, 20, 30 minutes long. So that's why I'm talking so fast here, but you can always pause it, think about what I say, and then if you can make it to an online Zoom meeting class, we can have kind of face-to-face conversations about these ideas. Okay, so let's get started. Breaking it down into these 4 goals. So give me a field F. All right, so by a polynomial in F, what I mean is a formal expression. So by a formal expression, I mean, don't think of this as a function or anything. I'm just saying by a polynomial, P, I'm going to write it like function, P of X, I'll call it, or just P. So what is it? It's a sum, A0, A1X, A2X squared. It looks like a polynomial. This might not look like a polynomial because I'm writing it as an infinite sum. The sum as I goes from 0 to infinity of AIX to the I. But I require that the AIs be an F for every one of those values of I. And then this is the important part. I highlighted it in red, that those coefficients are 0 for all but finitely many values of I. All right. So this is not really an infinite sum. All but finitely many of its coefficients are 0. It's just a convenience to write it as an infinite sum because then I don't have to keep talking about like what the last non-zero coefficient is. All right. So if you're a linear algebra veteran, you can just think that I've got maybe like a vector space, an infinite dimensional vector space. The basis vectors are things like 1, x, x squared, and so on. Those are linearly independent over this field. If you haven't had a linear algebra class, then some of this terminology might not be familiar, but I think it's worth saying to those who have. And then I'm just considering all vectors in that vector space, but I never write a vector as an infinite linear combination of the basis vectors, always a finite linear combination of them. I'll call the result a polynomial. All right, we're going to denote by capital F of X the set of all polynomials, P over F. All right, so in calculus and algebra, you were introduced to this polynomial ring where the field F was usually the real numbers. We looked at polynomials over real numbers. Okay, so good, we know what a polynomial is. It's kind of an infinite formal sum all but finitely many which of the coefficients are 0 in any given one of them. So what do I mean by two polynomials being equal? Here I'm giving myself two of them. P is polynomials whose, oh, I didn't mention this. Sorry, I think I wrote it. The numbers AI, or the field elements AI rather, they're called the coefficients in the polynomial. So two polynomials are equal if and only if their coefficients are equal. All right, so P is a polynomial, it's a formal sum. Q is a polynomial, it's a formal sum. P and Q are equal if and only if coefficient by coefficient. A0 is the same as B0, A1 same as B1, A2 same as B2. If they're ever different, they're different polynomials. If they're always the same, they're the same polynomial. In particular, we're going to call the 0 polynomial. I'll just simply denote it by 0. It's the polynomial whose coefficients are all 0. All right, so there's one polynomial whose coefficients are all 0, and we're going to call that the 0 polynomial. I'll mention this below, but I think it's a good time to mention it here as well. If you give me some element of f, then I'll think of that element as a polynomial. It's the polynomial whose 0th coefficient is your element, and the rest of the coefficients are 0. Okay, I'm going to call those things constant polynomials. I'll mention this again below. I've already written out these notes, but so I can think of f itself as a subset of the polynomials. It sits in the polynomials as the set of constants, polynomials that don't have any x's or x squareds or so on, constant polynomials, right? So I'm framing this in this kind of formal setting, but hopefully it all feels sort of familiar. You know, these are just polynomials. Good. How do we add them? Well, you know how to add polynomials as well as I do. If you're given two polynomials, say P and Q, notation defined above. Sorry, I'm scrolling all over the place, but I'm going to use this throughout the lecture, that P is a polynomial whose coefficients are called A's, Q is a polynomial whose coefficients are called B's. So how do we add them? Well, just like you learned in high school, you add polynomials by gathering like terms. So you add the constant term, you add the coefficients of x squared, and so on. That produces a polynomial because if both P and Q have all but finitely many coefficients that are 0, eventually out here in the list, you're just going to be adding 0 plus 0, 0 plus 0, 0 plus 0. So that's what I'm writing here, is that AI is 0 for all I greater than or equal to some number. I'm just denoting that number by n sub p, because it depends on the polynomial p. And bi is 0 for all I greater than some number n sub q, depends on the polynomial q. So the sum of ai and bi will be 0 as long as I is bigger than the maximum of those two numbers. So the sum of two polynomials is a polynomial. Cool. So you add polynomials by adding the coefficients, just like you always have. How do we multiply polynomials? Well, it's more complicated. This formula I'm going to write down, maybe it looks unfamiliar to you, you're looking at it, but you multiply polynomials the way you always have. You distribute and gather like terms. So you want to multiply two polynomials together, okay, crank it all out and gather like terms. This formula I'm writing, I've just gathered the terms. If you multiply P and Q, same notation as above, well, the constant term is the product of the constant terms, yeah? The linear term, the term that is in front of x, well, you could get that by taking a0 times b1 because b1 has an x in it, or a1 times b0 because a1 has an x in it. The quadratic term can come about in three ways. A0 times b2 because b2 had the x squared, a1 times b1 because x times x is x squared, and a2 times b0 because a2 had an x squared, and so on. So you can kind of see a pattern there. Here, the general coefficient of xi, ci I'm calling it, it's just the product a0 bi, a1 bi minus 1, a2 bi minus 2. Notice in that pattern, as the exponent clicks up, or the subscript rather, clicks up on a, it's clicking down on b. They always add up to I. That's all the ways you could get an xi when you expand out your formal product. All right, so that's how we multiply polynomials. I didn't say this above, but it's certainly the way we're going to use it, that when you multiply, say, a power of x by some other power of x, we're just going to use the usual rules of exponents. Okay, so short story, you add and multiply polynomials like you always have. Here's the part that I'm not going to write. I mean, technically speaking, this needs to be proved, but it's just a long, tedious computation. But this set of polynomials with those two operations is a commutative ring. The field operations of addition and multiplication are both commutative. So so all the polynomial multiplication is going to be commutative. And it's a commutative ring with unity. The unity is the constant polynomial 1. Yeah, you multiply a polynomial by the constant polynomial 1, you get that other polynomial back. So I'm not going to write out a formal proof of that, but maybe you could pick one axiom. I don't know, the associative of addition or the distributive laws if you want to go for something a little heavy hitting and just try to convince yourself that it works. It all works because the coefficients have those properties. And at the end of the day, we're multiplying and adding polynomials by doing those operations in the field. All right, so maybe it's a little bit hand wavy, but it's not worth I think getting bogged down and trying to write down a formal proof. I have a handout, if you remind me, you can ask me, where I typed up one time the proof that the distributive law holds in the polynomial ring. So if you want to check out my handout sometime, remind me and I'll send you a PDF copy of it. Okay, so let's just keep moving here. So I want to make a definition. Given a non-zero polynomial, I really want to emphasize that. I'm going to emphasize it by highlighting it in some alarming color. A non-zero polynomial. Okay, I define its degree, the degree of a non-zero polynomial. Ah, sorry, I'm having my little hiccup here. The degree of a non-zero polynomial, well, it's the largest exponent, the largest index n, such that an isn't 0. And such an exponent exists because if your polynomial p isn't 0, it has to have a non-zero coefficient, and it has to have a last one, quote unquote. There has to be a largest n where an isn't 0, and then it is 0 after that. The coefficients are 0 after that. So this is exactly what you think of as the degree. The degree of a non-zero polynomial is just the exponent on the term that's got the biggest exponent, right? The zero polynomial just doesn't have a degree. It's not degree 0 in particular, okay? Degree 0 means you're a non-zero constant polynomial. Maybe we should write that together. Or I've already written it, sorry. Zero polynomial together with the polynomials of degree 0, that is the non-zero constants. They make up the set of all constants. So it's kind of for technical reasons, but you got to kind of make peace with this, that constant polynomials come in two flavors. They come in the flavor, the ones that have degree 0, those are the non-zero constants. And then the zero polynomial, which has no degree. Okay, the zero polynomial has no degree. So here I'm writing it again. We think of the field as just a subset of the polynomials. It's the subring. You can prove that if you want. It's closed under addition and multiplication and all that good stuff of constant polynomials. And I know I'm going fast and I'm kind of throwing all these things at you, but really all I'm just saying is if you take two constant polynomials and add them together, you get a constant. If you multiply two constant polynomials together, you get a constant polynomial. The additive inverse of a constant polynomial is a constant polynomial. These things are not foreign to us, but it's just I'd rather kind of move through this and sort of get to something interesting to get bogged down in writing all kinds of formal proofs of things that are kind of obvious, and we know this stuff from our experience. However, I don't mean to downplay the kind of rigor in mathematics. It's usually not a good idea to just kind of wave your hand at something and say, oh, well, that's obvious. But here, I guess instead of saying it's obvious, I'm just saying it's true, and I don't want to take the time to kind of write out every last detail of this stuff. You're always welcome to ask me about any of it in an office hour or a meeting that we schedule. I'd be happy to start to write these details. But in terms of kind of general class, making these video lectures, I'm not going to do it. Okay, so we're down to the fourth part. I want to show you that the polynomials form an integral domain. And to do it, we need this kind of key lemma. So the lemma, I'm using the same number as the author. It's 4.5.2, and it says the following, that, and this again should sound very familiar. If you take two non-zero polynomials and you multiply them together, the degree of their product is the sum of their degrees, right? And you know this from high school. If you multiply a degree 2 polynomial by a degree 8 polynomial, you're going to get a degree 2 plus 8 or a degree 10 polynomial, because those leading terms are going to multiply and the exponents add. That's basically the proof. Here, let me try to write it down, I guess, slightly more formally. So let's look at our notation. Let's take P and Q, and notice that I'm not writing them as infinite sums, and I'll do this all the time because all but finitely many of the coefficients are 0. So I just write the last non-zero one. All right, so I write P with coefficients A's and Q with coefficients B's, and then I just indicate that AN and BM aren't 0, and N is the degree and M is the degree of Q. So that means that if you were to write more coefficients, they would all be 0. So you can write plus 0 times x to the n plus 1 plus 0 x to the m plus 1. But in general, we just sort of want to shorten the notation. We don't need to write all of that. You just indicate that these things are the degree. N and m are the degree. So by definition, n is the largest thing with the non-zero coefficient. Okay? I know I'm talking fast. So if you take some index that's bigger than n plus m, okay, then if j plus k adds up to that number, then either j is bigger than n or k is bigger than m. Maybe that's something that I should write up and have you prove as an exercise, but I'll just say it out loud right now. By contrapositive, if j is less than or equal to n and k is less than or equal to m, then their sum would be less than or equal to n plus m. So it couldn't equal I. So that's the statement of that. So when we look at the ith coefficient, remember these subscripts always add up to I, right? I minus 1 plus 1. So if one of those subscripts is smaller than the degree, like let's pick on the A's. If the subscript j here, this says this is my j and my k. If j is less than n, then k is bigger than m. So that product is 0. This product will be 0. As soon as the subscript on A, as soon as the subscript on B gets small enough to not be 0, well, then the subscript on the A's is big enough that it is 0. So every one of those products is 0, and you add 0 to itself a bunch of times. I didn't complete it, I guess. You get 0. All right, so what does that mean? That means that when you multiply these two polynomials, when you're past the x to the n plus m term, all of the coefficients are 0. So where are we in our proof? We know the degree is no more than n plus m. But by the same argument, the coefficient of n plus m is just going to be the product of the leading terms. If you let I equal n plus m up here, then the only non-zero coefficient you're going to get is when the subscript on A is n and the subscript on B is m. Because otherwise, to add up to n plus m, one of them would have to be bigger than the degree of the corresponding polynomial, yeah, to compensate for the other one being smaller than it. So that's the end of the proof. We have a non-zero polynomial because it has a non-zero coefficient. And beyond that coefficient, n plus m, all of the other ones are 0. So the degree of this thing is n plus m. That's what the lemma said. All right, we can talk about it in class, but I'm going to kind of keep this brief for the video. And now finally, the last thing, the author calls it a lemma, so I will too, but if this were my book, I'd call it a theorem, that the polynomial ring is an integral domain. I was kind of writing fast in addition to talking fast when I wrote this out, so I could have made this last sentence first, but we know that the polynomial is a commutative ring with unity, or at least I claimed it without proof earlier in this speed talking lecture. So all I need to do to show it's an integral domain is show it has no zero divisors. Okay, well, the recipe for that is suppose I have a couple polynomials, neither one of which are 0, and I want to show you their product can't be 0. Well, if they're not 0, then they both have degrees that are at least 0, because the only polynomial that has no degree is the 0 polynomial. And what we just proved is the degree of their product is the sum of their degrees, which is at least 0 plus 0, which is 0. So this product has a degree. Yeah, so the p times q cannot be the 0 polynomial if its degree is greater than or equal to 0. So p and q aren't 0 divisors. Okay, so I know that that was fast, and there's a lot to digest. So just keep telling yourself that you know what polynomials are, you've worked with them your whole life, and in terms of this long section, maybe it would be helpful for me to say, I think you should read, if you haven't already done so, section 4.5 in Herstein. And what I just covered was the material that begins on page 151. And we just made it to, well, lemma 5.54 is basically page 154. Okay, so take this video, maybe pause it a couple of times, maybe watch it again, and then check out the way Herstein describes this stuff to get used to the notation. And then the next video, we're going to talk about polynomial division. All right, thanks for listening.